Welcome to the Supercritical Fluid Technology series. In this opening chapter, we'll explore the fundamentals of supercritical fluids, one of the most fascinating states of matter. A supercritical fluid exists beyond the critical point, where the distinction between liquid and gas completely disappears. This unique hybrid phase combines the best properties of both states, opening doors to revolutionary applications in extraction, chromatography, and materials processing. Let's begin our journey into this remarkable field. So, what exactly is a supercritical fluid? The definition is straightforward. It's any substance heated above its critical temperature and compressed above its critical pressure simultaneously. When both conditions are met, something remarkable happens. The substance enters a state that is neither truly gas nor truly liquid. It possesses gas-like diffusivity, meaning molecules can move rapidly. It has liquid-like density, giving it significant dissolving power. And crucially, it has zero surface tension. This combination of properties makes supercritical fluids incredibly useful for industrial applications. Let's understand the critical point more deeply. Imagine heating a sealed container of liquid. As temperature rises, the liquid expands and becomes less dense, while the vapor above it becomes denser. Eventually, you reach a temperature where the densities of liquid and vapor become identical. At this point, the meniscus, that visible boundary between liquid and gas, simply vanishes. The two phases merge into a single, homogeneous supercritical phase. This transition occurs at specific temperature and pressure values unique to each substance, defined by thermodynamic conditions where density fluctuations diverge. The phase diagram provides a complete picture of how matter behaves under different conditions. Looking at a pressure-temperature phase diagram, we see distinct regions for solid, liquid, and gas phases, separated by boundary lines. The liquid-gas boundary terminates at the critical point, beyond which lies the supercritical region. Notice how this region is continuous with both liquid and gas. There's no phase boundary to cross. This is fundamentally different from transitions like boiling or freezing, which require crossing a phase line. The triple point, where all three ordinary phases coexist, is also marked on this diagram. The properties of supercritical fluids truly sit between gases and liquids. Consider density. Gases have about 1/1000th the density of liquids, while supercritical fluids achieve densities from 1/10 to nearly equal that of liquids. Viscosity in supercritical fluids is much lower than liquids, closer to gas values, enabling rapid mass transport. Diffusivity is similarly enhanced, with molecules moving much faster than in liquids. And critically, surface tension is zero above the critical point. This property combination explains why supercritical fluids are such effective solvents and why they excel in extraction processes. Many substances can become supercritical, but their critical conditions vary dramatically. Carbon dioxide is by far the most commonly used, with a critical temperature of just 31 degrees Celsius and pressure of 7.38 megapascals. These mild conditions make CO2 accessible and safe. In contrast, water requires extreme conditions, 374 degrees and over 22 megapascals. Ethanol and propane have intermediate critical points. The choice of supercritical fluid depends entirely on the application. CO2 dominates due to its accessibility, safety, and environmental benefits. Carbon dioxide has become the gold standard of supercritical fluids for several compelling reasons. Its critical point is just above room temperature, meaning you don't need to heat materials significantly, protecting heat-sensitive compounds. The critical pressure, while substantial, is achievable with standard industrial equipment. CO2 is non-flammable and non-toxic, eliminating fire and health hazards. It carries a GRAS designation, generally recognized as safe, making it acceptable for food and pharmaceutical applications. As a greenhouse gas that can be recycled, using captured CO2 for extraction actually provides environmental benefits. Recent research has challenged our fundamental understanding of supercritical fluids. In 2025, advanced simulations and experiments revealed that supercritical fluids are not perfectly uniform as long believed. At the nanoscale, they contain transient clusters of about 30 molecules, roughly 1.3 nanometers in diameter, that briefly form liquid-like structures before dispersing. These clusters persist even above the critical point. This discovery has significant implications for understanding extraction selectivity and nucleation processes, opening new directions for research and potentially explaining previously puzzling behaviors in supercritical systems. The science of supercritical fluids has a rich history spanning 2 centuries. In 1822, Baron Cagnier de la Tour first observed the disappearance of the liquid-gas boundary when heating sealed tubes. Thomas Andrews conducted systematic studies in 1869, establishing the concept of the critical point. Hannay and Hogarth discovered the remarkable dissolving power of supercritical fluids in 1879. Van der Waals' equation of state, which earned him the Nobel Prize in 1910, provided the theoretical framework. Commercial applications began in 1962 with Kurt Zosel's caffeine extraction patent, leading to the first industrial decaffeination plants in the late 1970s. Today, supercritical technology is a multi-billion-dollar industry. Let's summarize Chapter 1. A supercritical fluid exists when temperature exceeds the critical temperature and pressure exceeds the critical pressure simultaneously. The phase diagram shows the critical point terminating the liquid-gas boundary. Supercritical fluids combine gas-like transport properties with liquid-like density. Carbon dioxide is the preferred supercritical fluid due to its mild conditions of 31 degrees Celsius and 7.4 megapascals, combined with safety and environmental benefits. The 2025 discovery of nanoscale clusters challenges our uniformity assumptions. These fundamentals underpin a green chemistry revolution across many industries. In Chapter 2, we'll dive deeper into supercritical carbon dioxide specifically.